Okay, we're finally ready to get started again. So let's get started. So is everybody okay with HMS? Are there any questions about how to set up an HMS model? Did you? It looks like everybody was able to work through their problems. So hopefully that's okay. We're going to go ahead and talk about long-term simulations with HMS and how to do long-term simulations. So this is, if you don't have just a single storm event, then you can do multiple storm events with HMS. We're going to talk about how to do that. If you're doing a long-term simulation, there are a couple of things that are going to be different than just a single storm event. One of the things that's going to be different is your precipitation. Your precipitation is long-term precipitation instead of just a single hyetograph or a single curve for precipitation. The other thing that's going to be different is your losses in your base flow is going to have to be defined differently for a long-term simulation. And this includes, so your losses, you're going to have to include losses in your canopy, surface and soil losses, and also groundwater losses. And there are a bunch of, and also you have to include your evaporation and transpiration. HMS uses something called the soil moisture accounting, or SMA method, for long-term simulation. So this is the method you're going to use, and this is a picture of the different layers. So we're starting at the very top, that's the ground level, and you're looking at canopy storage, surface storage and then when you go below the ground, you have an upper soil zone and a lower soil zone, and then beneath that you have groundwater 1 and 2 storage. And so these are the different layers. There's 5 different layers that are used in the SMA, or soil moisture accounting method, that's in HMS. And let's talk about some of the input parameters. So this is a list of the input parameters that are used in the SMA method. You have to define all of these parameters. And your slides are going to have some starting values. So later on we're going to run through a sample SMA method calculation, and your slides are going to have some sample input values for all of these things. So let's look at each of the layers individually. First of all, there's the canopy storage layer, and this layer includes evapotranspiration. And well, first of all, the precipitation goes into the canopy, and while it's raining, there is no evapotranspiration, or HMS assumes there's no evapotranspiration when it's raining. But after the rain stops, there can be evapotranspiration. There's something called canopy overflow, and so that's the canopy. So that's kind of above the soil, like in the leaves and things like that. Beneath the canopy, you have surface storage. So you have canopy overflow coming into the surface storage. You have evapotranspiration out of that layer. You also have surface runoff. So your surface runoff comes from that layer as well, and then some of the rainfall goes into infiltration. Your next layer is your upper and lower soil storage areas, and you can get evapotranspiration from that layer also. The input for that layer is your surface infiltration. The output is your percolation and evapotranspiration. And these are the equations and relationships that are used in this layer, and your notes explain what all of these variables mean. It's kind of confusing. Yeah.
The layer, how can I define the thickness of this layer? If there's any document the input.
How do you determine the thickness? So
I don't know.
Yeah, I don't know. It's there's really no way. I mean, there's no data that is available to determine the thickness. So what you have to do is just calibrate your model, either manual or HMS has an automated. What's that?
I'm going to calibrate to parameter.
Yeah, so just have a starting thickness, then you're going to calibrate the starting thickness value. You'd use that as a calibration parameter. If you don't know, there's no way to know what the thickness is. I mean, other than I guess you can go and start digging the soil, but even then, there's no way to determine the thickness. So, yeah, that's.
I mean, this type of parameter, I want to know the thickness. What is
You want to know.
mean, so I can assume the this parameter. How can I find the value for all parameters?
So how do you determine the thickness of this layer and all of the other parameters? Well, there's no. We have no way of determining these parameters. So you have to have just some values that you think might be correct. And if you look through the slides, so here toward the end, we have these starting parameters that you can use. And then in the workshop, there are some other parameters, but just use these parameters. So the soil layer thickness is right here, and you could use 10 inches, 254 millimeters. But I don't know. That's a good starting value. Start with that and see what happens.
This is the only method available in
For long-term simulation. So if you're doing a long-term simulations, this is the method that you have to use. And what I usually do is just start with these parameters and then calibrate my model, get it as close as possible to what, if I have calibration data, I have to calibrate my model to these. Yeah.
She has the actual data. She passes how she can insert it in the model, isn't it?
No.
I hope we will have to insert.
We don't have actual data. How we can solve this problem?
You know, when I try to calibrate, when we put a start value, the model run around this value. If I change, give it the another value equal to the start value. I don't know. I noticed this in using when I go to the start value, maybe write 10. Run and give me the value write 10.5. If I change the 10 to 20, it gives me like 21.
So it finds a value that's close to your starting value.
Yeah.
Okay. Yeah, and that's just the method that's used for calibration, because it's a local calibration method, which means it doesn't do a global search. It doesn't search all the range of values. It's just a local calibration. So you'd have to manually change that value and then run your calibration for a variety of different values.
I have to be close to the real value and get
Yeah. And I mean, these values are not, they may not be, there's no way to get these values. I mean, I don't know how you're going to compute these values. There's no data available. And so you have to make them up. You have to make up the values, and you have to calibrate your model somehow. And so, like, if you're modeling the Nile River, right? You're doing a long-term simulation on the Nile River to figure out the flow rates. You're going to have to get some observed flow rate data from the Nile River, long-term flow rate data, and calibrate to that. Change these values. Just get as close as you can to the observed data. And so you have to just change the parameter. And then you can forecast for the future based on what's happening in the model. But I don't know that these parameters necessarily have to be accurate. You just have to, your observed data has to match the computed data. If you can get the observed and computed data to match, then you'll be fine. And don't worry so much about how to get the parameters, I guess. You just want to be able to calibrate your model in the long run. So I'm just trying to show you how the model works, and let's not worry about where we get the parameters, I guess. Let's just always start maybe with these parameters right here, and that's a good starting point. Okay, so you have soil, the soil layer. These are the relationships that are used in the soil layer. I'm not going to get into the details of that, and then you have your groundwater 1 layer, and Q is in the groundwater I have this percolation from the soil layer. So the soil layer has percolation coming out of the soil layer. That goes into my groundwater layer. And then I have an outflow, which it goes into the base, it can eventually go into the base flow. Then I have percolation to another layer. And so this is how my outflow is computed using this equation. This is how my percolation is computed. And your notes are going to have on your notes, it has what these values are. So this slide here, it's kind of hard to see it on the overhead, but it explains what all of these, the S, and then the P and ET. So ET is evapotranspiration, I is infiltration, P is percolation, and the S represents storage, so that's the amount of water in each of the layers, and T is just time, I is infiltration like I mentioned. So anyway, all these things mean something, and you can just plug in these equations and compute the value if you want to compute the value, or you can just HMS computes the values at each of the time steps in your model. So you have your soil, your groundwater 1 layer, and then your groundwater 2 layer. And the groundwater 2 layer takes water from the groundwater 1 layer, and you have an outflow from this layer. And then anything that goes down from this layer is called deep percolation, and it's lost to your model. Okay, so you'll never see the water that is lost to deep percolation. So some of the things to remember with this SMA model, the long-term simulation model, is that evapotranspiration only occurs when there's no rainfall. And evapotranspiration also occurs from 3 of the layers. It occurs from the canopy, the surface, and then the soil layers. The soil percolation only occurs when the tension zone capacity is exceeded. And what that means is there's an input parameter called the tension storage. So when this amount of water is in your soil layer, so 6 inches in this case, if my soil layer has more than 6 inches of storage in that layer, or 152 millimeters, then if that's exceeded, then I'll get some percolation into the groundwater. Percolation from the groundwater 2 layer is totally lost from the model. So anything that goes out of this bottommost layer, deep percolation, that's completely lost. You'll never see that water again. Okay? So if I were to do this by hand, if I were to compute the amount of water in each of my layers by hand, these are the steps I would take. First, I would add my water from the precipitation to the canopy and the soil surface. Then I'd do my evapotranspiration calculations. Then I'd compute my infiltration and percolation rates for each layer. I'd run my groundwater outflow calculations, and then calculate my surface runoff storage and storage for each subsurface layer. So I follow those 5 steps if I want to compute by hand. And so I have this example. I'm not sure that we're going to, I was thinking maybe we would have everybody do this example, and it has you go through, and for 3 different time steps we can compute the amount of storage in each layer. So I'm not sure I'm going to have you do that because it takes a lot of time. I don't know if we do. Are you guys interested in doing that, computing by hand the amount of storage in each of these layers? Or will you just want to run HMS? You don't want to do it? Did you have a question? Yeah. Well, why don't... Okay, why don't we... How about let's just go ahead and do it. So here's the problem. These are the input parameters for your problem. Okay? And at the first time step in my model, these are the amount of storage in each of my layers. So my canopy has 0.05 inches, surface has 0.15 inches, soil is 9 inches of storage, and these are all the amount of the inches of water in each of these layers. And then I have this amount of water in my groundwater 1 and this amount in groundwater 2. When at the second time step, I'm going to run through that, and so the first time step I have 0.05 in my canopy. The second time step I get 0.2 inches of rainfall. And you follow those 5 steps for this time step. So these 5 steps back here, these computation steps, and for the first time step I get these values. So 0.1, 0.29, 9 point something, it's kind of hard to see that, 4.35. So those are my values for each of the layers. And these are how I do the computations. At the second time step, I get these values. And the third time step, I get 0.4 inches of rainfall coming in, and it's your job to compute the amount of water in each of the layers, okay? So why don't we try to do that? You have this workshop. If you go to your, let's see, go to your PDF files, and we're looking at HMS Long Term. Actually, Long Term Basic is what we're looking at. And then if you just go through these slides, so we are on the third time step, so 3 o'clock in the afternoon, and these are this is the inflow, this is the amount of precipitation, 0.4 inches at that time step, and you have to compute, and this is the previous time step right here. So your job is to compute the amount of water in each layer at this time step. And so you can, it's kind of hard to read these, but you have 0.1. Are there any questions? So we're going to take 15 minutes and maybe get out a piece of paper, if you have some paper, draw each of these 5 layers and draw the arrows, and you just need to compute I think so, yeah. We'll try. Whoever can do it first wins, I guess. So maybe draw this picture on a piece of paper and figure out how much water is in each of these layers. And I can make this the first time step, so I'll make this previous time step bigger so we can see what's happening. I'll just increase the size, the resolution.
Do you think it's important to do it manually, or we can do it using the HMS? Better.
I think it's useful, so I think it's useful to do it manually. Let's take 15 minutes and do it, and we'll see what happens. Okay? And
50 minutes will be 100 minutes. If you want not 50 minutes.
okay, we're gonna start up at 10:05. We'll continue on this lecture at 10:05. So take 15 minutes, and we'll see how it goes. Okay? So just get out a piece of paper and draw these layers, and we'll figure this out. Are people complaining?